Well, we are still batting 26 not out, and so today we'll continue with what we did last time. I'll just recap the pure lambda calculus. So here's the syntax of the pure lambda calculus, and in the case of the applied lambda calculus you just add a constant. We'll come to that. This is the standard definition of free variables, the notion of a combinator or a closed lambda term, which is according to our local declarations. Whatever we know about local declarations, it's all equally applicable. And here's the operational semantics for beta reductions. So there is of course the important thing to realize that is this syntactic substitution. So we have these usual rules. So this is the main rule, which says that note that this operation is not part of the lambda calculus, it is the syntactic act of replacing one pattern by another. So it's what might be called a meta-syntactic operation. Yeah. Then of course we close these rules in various contexts, including the abstraction. If you don't have the abstraction, then it becomes what is known as a weak beta reduction. Such a term, which is an application of an abstraction to a lambda term, is called a beta redex, and you can generalize this to, you can take transitive closures of beta redexes of beta reductions and thereby get many step beta reductions, either strong or weak. You can also take the equality that is generated by a beta reduction by many step beta reductions, and you get, well, an equivalence relation. And since the beta reduction rules are closed under context, actually this equality is actually a congruence relation. And then here's an example of an applied lambda reduction. So using piano arithmetic. So as I said, so we went through this last time. As I said, we could equally well have chosen other possible beta redexes. I mean, there could have been several beta redexes. We could have mixed beta reductions with whatever piano reductions in any order. But even if you were to take the pure lambda calculus, what it means is that firstly is that the lambda calculus by its very semantics is an inherently non-deterministic, possesses non-deterministic execution behavior. So there are other possible execution sequences for the same lambda term, especially when you have two different beta redexes. So what it means is there is no hard and fast rule which way your non-determinism will, which way, if you had an executor, which way it will take, unless you determinize the executor and take up scheduling policy, it's really non-deterministic. It's essentially non-deterministic. And when you couple it with in an applied lambda calculus with maybe non-determinism from the domain, applied domain, of course our piano arithmetic was not non-deterministic. If you look at the reductions in the piano arithmetic, they are purely deterministic. So it could become even more non-deterministic. Okay, so as far as the basic computations are concerned, it's clear. The only thing that's not yet clear is what exactly is all this lambda calculus about. So let's look at how we can interpret lambda terms, and which is essentially the original agenda which Church had set out to himself, right. So let's look at the operator that, let's look at this lambda term. It's a mixed lambda term with piano terms in it. So what does this do? This says lambda x, lambda y, star xy. Okay, the star xy is clearly a piano term which denotes multiplication. Remember that in our normal multiplication, which is also what is there in piano arithmetic, the multiplication is a binary operation which takes two arguments, right. Now here this lambda abstraction makes it a function of a single argument where the arguments are taken in sequence. So, the effect of essentially applying this lambda term to the natural number 2 is to create a new function which is the doubling function. Okay, so given any natural number, it will double it, right. So that means this x will be substituted by this 0 double prime, and you get the doubling function. And of course there are, well, you could define the doubling function independently itself in some such fashion, but the point is that this is what is known as a curried form of the multiplication operation. We will get into currying a little in some detail a little later, but the effect is that instead of the lambda calculus treats every function as a unary function, and the way to program binary functions or n-ary functions is to allow for a sequence of abstractions so that the arguments can be taken one at a time. Okay. So this is essentially a binary function which requires 2 arguments before you can get a value, but those 2 arguments are taken in order one at a time. So you first apply it to the first argument and you get another function which when applied to another argument will give you a value, right. So this function is obviously a unary function, and so is this. I mean, so there is no problem about that. Now if you look back at this example, at this previous example, we could actually give a name to this function. So I am taking this lambda term and I am calling it twice, right. So it is lambda x, lambda y, x applied to y, right. What is the behavior of this twice? I mean, what does this twice actually mean? It means that supposing now we have nothing except just variable symbols, and we do not know whether those variable symbols denote values or functions or I mean anything, or functions of functions, higher order functions, anything. So now if you were to take this and apply it, let us say, to the doubling function or to one of the 2 doubling functions, right. So take this twice and apply it to one of the 2 doubling functions, right. And what you will get is so I have used the word double itself to denote this function. So when you apply twice to double, you follow the normal beta reduction rules, and what you get is that you get double y which is applied to double, or rather double is applied to double y, and which is the quadrupling function, which makes perfect sense, right. So if you were to take I mean you could this is of course a simplistic way of looking at things, you could actually take the expansions out. After all, remember that one of the purposes of the lambda calculus is to treat unnamed functions, right. I mean, to look at functions themselves as objects worthy of treatment, surgical treatment maybe. So if you were to actually do this application, what you get is, again you get actually a non-deterministic choice between 2 possible beta redexes. So this is a twice applied to the double, and the effect of that is to replace all these blue x's by this term. So that is what comes out in red, and of course this y is here. Now either I have the possibility of replacing these 2 x's, note that this is an application, an open parenthesis followed by a open square bracket. So I have the possibility of replacing each of these x's by this entire application, or I am taking an easier way out to avoid confusion, is that I am first doing this application to, so I am leaving this term as it is and I get this, a nice neatly simplified term, and then I when I apply this, when I perform this beta reduction, I get this, right. So this is the quadrupling function, which is perfectly understandable, and actually if you look at this definition of double, it really does not matter what you put here. I mean, if you did not put double, you could have put something else. For example, you could have put, for example, the squaring function. So twice of square, for example, should give you just, well, the square of the square, and the square is very easily defined as a unary function, and I could just get the square of the square. So we could actually put any function in place of double or square and apply twice to it. So in particular, what I could think of doing, and which Church did, unlike most mathematicians who are scared of doing such things, is that he applied twice to twice. This is normally not found in mathematics, but if you are talking of a purely symbolic method of computation and functions and this and that, then what it means is that you should allow for such a possibility and see what you get. So when you apply twice to twice, you get this, you of course get, well, twice applied to y. I mean, which is perfectly reasonable. So if you, in fact, if you were to apply it to double again, what you would get is twice of double and twice of that, which is the octupling function, if you like. I mean, this is, by the way, this is my name. I'm sorry to say that natural languages don't have enough names for my purpose. So this is the function which goes 8 times, let's say, and it's a perfectly reasonable function. So why are mathematicians scared of applying a function to itself, right? So then what happens is that I could look at this twice, okay, and what I could do is I could actually look upon this application of twice to twice as actually a lambda abstraction applied to twice, right. So this is this particular lambda abstraction, which if you do a beta reduction, each of these x's will be replaced by twice, and of course the abstraction x will go away, so you will get twice applied to twice, right. So which means that there is a way of getting this twice applied to twice by another lambda application, okay. So now this becomes an object of interest in itself. So what I could do is I could play the same game, apply this function to itself. So I apply it to itself, and what do I get? Each of these x's is going to be replaced by this term, and I get this, which except for the color is exactly identical to the previous term, right. And so you do this application, and again you get exactly the same term, and so on and so forth. So then this was an example of a non-terminating computation, right. So what Church, going back to Church, what Church essentially did was he said that an algorithm, what is an algorithm? Well, an algorithm is an abstract object which is totally meaningless as far as I am concerned. If you want to give a logical definition of an algorithm, it is a lambda term which has a terminating computation. The only concrete representation of an algorithm is of a lambda term which has a terminating computation. So of course you should make a distinction between this non-terminating computation and say a computation of this form, say a term of this form itself. I mean, take this lambda term. This lambda term is an algorithm in the sense that, well, the computation is already terminated. I mean, there are no more beta reductions possible, but this lambda term is not an algorithm because the beta reductions are possible and it is an infinite computation, right. So essentially Church said that, so the concept of an algorithm is just, so if you look at it in more modern terms, what it means is what Church has constructed is a full-fledged programming language. What he claims is that the notion of an algorithm, though 2000 years old, is not an accurate notion in any sense. It is only a notion that could be understood by intuition. The only concrete objects are not algorithms but programs, and algorithms are simply programs that are guaranteed to terminate. There are programs which are not guaranteed to terminate, yeah, which can have infinite computations. So that essentially settles the issue of the notion of computation, the notion of algorithm. Gödel did not quite believe what Church said, but the point is that it was what Church's work was subsequently complemented by Turing's work, and the two formalisms were proved equivalent and so on and so forth, which you will learn in your theory of computation, hopefully. Okay, now we have to worry about some other aspects of our theory. Let us get back to the beta reduction, which is, well, the most important thing in life. So you have this syntactic substitution, right. So which is replacement of a variable by another lambda term. So now so if you play around with the lambda calculus as a sort of toy, which of course my children frequently play with the lambda calculus as a toy, is that for example I could take this lambda term, which really denotes the multiplication operation in the lambda calculus, in the mixed lambda calculus, right, or rather in the applied lambda calculus, mixed lambda piano calculus if you like. And then what I do is, so essentially I can look upon this lambda term as a box that I acquire from somewhere. Typically you acquire a box like this from the US, and then you have this 110 volts 220 volts problem. So then you go to Jackson Heights or Kotla Mubarakpur or Lamington Road in Bombay and you get another box, and you apply one box to the other and hope and pray to God that it works, right. So here I have another box called Z, which I have acquired from Jackson Heights, and now I apply them in the hope of getting something that works, right, and actually it does. So I get a new box which is the function multiplied by Z, whatever Z might be. Then of course since Z is a Jackson Heights product, it is not very reliable, and after some time it conks out. Having detected that it conks out, I go to the local market and ask them to supply me a Z, but they say, well, we do not exactly have the Z, I mean, but we have something else which will work equally well, we have a Y, right. Okay, so you have a Y, so now I plug them both together, and what do I get? I get something, a typical Chandni Chowk product. I mean, right, I wanted multiply by something and I got squaring. Right, so that is the problem when you play around with these toys, especially when you play around with incompatible toys, right. So Church of course put it out more loftily and so on and so forth. He is not aware of Chandni Chowk and Kotla Mubarakpur and so on, and what he said was that essentially this Y that you acquired from the market is different from the Y, is really different, though it looks identical, is really different from the Y that is inside this box, right. And the two Y's, and these two Y's are actually different and they should not be treated as the same, and that is where the problem is. So essentially what has happened is that this Y is a free variable which has a value, which presumably has a value in some context, okay, maybe 110 volts, but the point is that the moment you perform this beta reduction, this Y gets captured by this locally declared Y. Okay, so a free variable gets captured even though it is not intended to be captured, right. So what it means is that now you will have to and remember that, so which means this notion of substitution in the operational semantics is something that has to be very carefully worded out, right. I mean you can't just do substitutions like this. I mean another possibility is supposing I have actually a lambda term of this form. If I have a lambda term of this form, something blah blah blah, to which I actually apply some substitution. This substitution came about as a result of some beta reduction somewhere. I mean this lambda term is part of some huge larger lambda term, and then I get this x should be replaced by m. Okay. Now the point is that this x should be replaced by m, this is not an application, it's a syntactic substitution, and this x is not the same again as this x. This x is very highly local to this box, and this x which was supposed to be replaced was some free x, some x that was outside this box, right. If this whole thing was part of some larger lambda term in which there was some reduction, I mean what I mean is, supposing I had this lambda term and then this lambda term is in turn a subterm of something else which has an x abstraction to which I actually applied an m, right. Then a beta reduction means that this x has to be replaced throughout this term, but if there are any local x's there, they are different from this x, right. So in the process of doing this replacement I might actually encounter this problem that I have to deal with a syntactic substitution of this form, and what do? Since this x is different from this x, I should not do any replacement at all, right. So this is again another instance of a free variable capture, except that this x is actually bound, but it has a scope, and this x is a hole in the scope of this x, right. To use our standard programming language terminology, this scope is actually a hole in the scope of this x, and as far as the body of this huge lambda term is concerned, the x is free, and you can, if you make this replacement, you might be capturing as far as just this body is concerned, this x is free and it will get captured, right. So the first principle of doing successful computations on the lambda calculus is not to allow free variable capture. So which means we have to define this notion of syntactic substitutions very carefully, yeah. And whenever we talk of substitutions, it is clear from our beta reduction rules that we are talking about only free variable substitutions and no other substitutions. No other bound variables are not to be substituted. Okay. Bound variables get substituted in a two-step kind of process. They get bound variables are like parameters to a procedure. You apply a value, you apply the function and you take the body of the lambda term which has this bound variable x, and then you do the replacement, but then the x in the lambda term is free, right. So, all substitutions that we will talk about are only free variable substitutions. So, unless otherwise mentioned, in fact I will not mention it otherwise too, all substitutions are going to be only free variable substitutions. You cannot replace bound variables because bound variables are logically distinct elements. Whatever you require to do in the sense of bound variable substitution is something that can be obtained through the normal process of lambda application, by first freeing the variable and then doing a free variable substitution, right. So, let us define free variable substitutions in as accurate a manner as possible. Now, this free variable substitutions has had a very rocky history. Okay. Most people, most books, let me tell you, are probably wrong. Okay. They have made a mistake somewhere or the other in the definition of these substitutions. So, do not believe most of these books, but play around with it to see whether there is a bug in my definition, right. Okay. So, if I have a lambda term x and I am going to replace x by m, then the effect of this syntactic replacement is just to give me m, which is perfectly obvious. If I have the lambda term y where y is different from x, then the effect of doing this syntactic replacement, so which essentially means replace all free occurrences of x in this term by m, and there are no free occurrences of x in this term, and therefore the result is just y, right. So, now if it is a constant in the case of an applied lambda calculus, well, a constant is different from any variable by definition, right. And so, the effect of this substitution is just to leave the constant unchanged. If it is a lambda application, if it is an if it is an application of L to n, then the effect of this substitution is to replace all free occurrences of x in this application by m, and that works out to replacing all free occurrences of x in L by m and applying the resulting lambda term to the term obtained by replacing all free occurrences of x by m in n, right. Okay. Now, that is also obvious. Note that these are all structural definitions by some case analysis. Okay. Here is where you get an important set of case analysis. If I have lambda x L, then this syntactic substitution clearly refers to an x which is different from this x, and therefore, there is no free x in this scope. There cannot be any free x in this scope L. So, the effect of this substitution is just to leave the lambda abstraction unchanged. Yeah. So, if on the other hand y were different from L, then the effect of this substitution is to replace all free occurrences of x in L by m, right. So, if, and moreover an added constraint here is that m itself should not contain any free variable, should not contain y free. If M contained y free, then the y in M is different from this locally bound y, right. So, you can do this free variable substitution only if y does not occur free in M. If y occurs bound in M, there is again no problem, because that binding will be carried through in the substitution. Okay. So, y has to be different from x, y should not be free in M. Now, the point, now what happens, so supposing y were occurring free in M, what would you do? Then what I would do is this: take this lambda yl and let me lower this so that I can still retain this. So this is a case very similar to the previous one, except that y does occur free in M, okay, but y is different from x. Then what I do is I pick out a new fresh variable z, and then what I do is I systematically replace, since y is a bound variable here, it probably does occur free in this term L. I systematically replace all free occurrences of y by z. Note that if there are bound occurrences of y, then they do not have to be replaced, but all free occurrences of y. So, I mean the same variable could occur both free and bound within that thing, within a lambda term, and obviously they are two different objects, right. So, all free occurrences of y in L are replaced by z. So, I get a new term which is, let us say, L prime by this, and now I do not have any problem. I replace all free occurrences of x in this new term by M, and I can do this provided z does not occur free in M. So, that is why I am saying take z completely fresh. Freshness is not a virtue that many of these books have emphasized, right, but it is the safest possibility. When in doubt, pick out a fresh variable, and there is no dearth of variables, because we have covered our tracks by saying initially assume a countably infinite set of variables available to you. Any particular lambda term is a finite syntactic object, and so has only a finite number of variables, it cannot have an infinite set of variables. So, therefore, you are always guaranteed that there exists a fresh variable that does not occur anywhere, right. So, you take a fresh variable, or at least take a variable that ensures that is such that it does not occur anywhere in the terms in which you are performing your substitution, right. And then first systematically replace this variable y, and this is the case when y belongs to the free variables of M. Systematically replace all free occurrences of y by z, and then in the new term systematically replace all free occurrences of x by M. Note that x itself could occur in M, either free or bound. So, these free variable substitutions are perfectly general if you follow this case analysis. Yeah.
So why is this condition required? Z does not belong to BV at union BV?
The problem is that I might have, this is the mistake that is there in many books. The problem, if I recollect right, is that you might have if Z is fresh, there is no problem. If Z is not fresh but occurs bound, in somewhere deep inside the term, and if z occurs bound, then you are going to replace, and you have z occurring bound in M also, and if I have some application like this deep inside, then the z that occurs bound in M, okay, that will not affect, but if the z occurs free in M, then there is going to be a problem. Okay. But the problem with these syntactic substitutions is, over 60 years it is very difficult to distinguish between what definition is right and what definition is wrong, and I am playing safe. So I am saying just take a new variable, don't get confused, don't allow for any possible confusion, just pick out a new variable that has never been used and do that replacement first. I am just playing safe. If you analyze some of the definitions, you might find that some of them are really correct, but you have to do a large amount of case analysis before you can prove them correct. Instead, I prefer to take the safe way out, okay, because of such things. For example, in Ravi Sethi's book, this bug is there. He just assumes that z is not free in M. But in the act of replacement there might be confusions between two bound z's, okay, as the x, okay, so that this confusion between two bound z's should not occur. I mean, that's something that I suspect he is not taken care of, right. So I would prefer always, as a good pragmatic rule, to pick out a fresh variable and do the replacement before doing it. In fact, what I would advocate is that the moment you see two lambda terms which have common variables, which have common bound variables, I would suggest that you just replace them all by fresh variables, and that is something that all students know offhand, right. So if you look at these terms, so in what way are the following different? So all these are, I have taken the definition of twice, and what I have done is I have just done various kinds of replacements. So here is lambda x, lambda y, x applied to xy, which was the original definition of twice. Now what I have done while going from here to here is I have systematically replaced all occurrences of x, not just free. I mean, what I mean is I have not performed the syntactic operation of substitution. I have just considered this as a string of symbols, and I have just systematically replaced all occurrences of x, whether free or bound, by u, and all occurrences of y, whether free or bound, by v. In this case, I have taken this and just replaced all occurrences of y, whether free or bound, by u. In this case, what I have done is I have done a simultaneous replacement. I have, with one hand I have replaced all occurrences of x by y, and with the other hand simultaneously, so that there is no confusion, I have replaced all occurrences of y by x. Okay. And in what way are they all different? Actually they are not different, right. So, and they are all the same, they are all obtained by what might be called the renaming of bound variables, right. and so essentially in addition, so we have, if you look at, so between so one possibility is that you have this syntactic identity. These 4 terms are not syntactically identical, but they are sufficiently identical in the sense that only the names of local variables are different, otherwise the patterns, the structure of the patterns is the same, right. And so we would consider them almost identical, and that is called alpha conversion. Yeah. So all these terms are really alpha convertible, and what is so my problem now is that I have, how do I express this alpha conversion in terms of our notion of syntactic substitutions, which we have rigorously defined, right. So for example, how do I get this 4th term from the 1st term? It is actually very simple. In 2 steps I get the 2nd term from the 1st term by two syntactic replacements using what I call alpha conversion, which I am going to talk about now, and then in another 2 steps I get the 4th term from the 2nd term. Yeah, right. So what is alpha conversion? We have to define that rigorously too. So alpha conversion is just this, just says that given a term of the form lambda xl, it is alpha equivalent, that means it is almost syntactically equivalent to a term in which there is a bound variable z and all free occurrences of x in L are replaced by z, where of course one thing that we should ensure is that if 2 terms are syntactically equivalent, syntactically identical, then they are also alpha equivalent. I mean that's a trivial thing. I mean, so this z is either the same as x, or again I am playing safe, z is a fresh variable different from anything in this term, and this is the safest game to play and not get misled by most of these books which only concentrate on free variables. It is possible to construct very often perverse and convoluted examples in which some of the definitions in most of these books will be proved wrong. It is also very hard to construct examples to show that they are wrong. But what is safe is always to pick a new variable, a brand new variable, preferably shining, yeah, and do the replacement, right. So the basics of the lambda calculus, which I hope you will spend some time toying around with. What is the basic of what does a calculus mean? I mean that's most we missed that out. I mean, why is Pascal not a calculus, whereas this language of lambda terms is a calculus? Why is it a calculus? What's a calculus?
It deals with computation.
What is a calculus about propositional logic? Why is it called propositional calculus? Why is it called predicate calculus?
Computation.
But in the propositional calculus and the predicate calculus, there are no computations unless you impose computations somehow.
It deals with variables.
No, a calculus is a system with a formal language, that means defined by something like a context free grammar, and whose rules of inference, whose axioms and rules of inference are such that there exists an algorithm to decide whether a given application of an axiom or a rule of inference is correct. A calculus is one in which, regardless of meaning attributed to a formal language, there exist purely syntactic rules, symbol pushing rules, which allow you to perform inferences. That is in fact a property of your axiom systems for first order logic, for propositional logic, for Boolean algebra, and the lambda calculus. The rules have to be purely syntactic and involve only symbol processing, and by symbol processing usually I mean just pattern matching and replacement. That is what makes it a calculus. Okay.